Welcome to Numerical Analysis. Have you ever wondered how a computer solves complex mathematical problems when it doesn't know the answer right away? It doesn't just magically guess the perfect solution on the first try. Instead, it makes an educated guess, checks its work, and then makes a better guess. Today, we are going to explore a fundamental concept called convergence analysis. This is the mathematical study of how those guesses get closer and closer to the true answer and exactly how fast they get there. Let us dive in. Now that we know what convergence is broadly, let us look at how it works. Imagine you are trying to tune an old analog radio. At first, you hear loud static. As you turn the dial, the static fades and you start hearing faint music. Every tiny adjustment brings you closer to that perfect, clear signal. In numerical analysis, this process of getting closer to the exact right answer, step by step, is called convergence. We start with an initial guess. If our method is working, the difference between our guess and the true answer shrinks with every step. If that difference does not shrink, the method diverges, meaning our guesses are getting worse and flying out of control. We need to guarantee our method converges. To understand convergence mathematically, we first need to define what a mistake looks like. This formula we just saw leads us to an important definition. Let us define the error. We use the letter P to represent the exact true answer we are searching for. We use x sub n to represent our current guess at any given step n. The error, denoted as e sub n, is simply the difference between our guess and the true answer. If our guess x sub n is exactly equal to the true answer p, then the error e sub n becomes exactly 0. This means we have found the perfect solution. As our guesses improve, the physical size of this error should decrease. Now that we have defined the error, let us look at the formal mathematical definition of convergence. We use the limit operator here. The symbol lim, with n approaching infinity, means we are looking at what happens as we take more and more steps, going on forever. The vertical bars around the error mean we are taking the absolute value. We only care about the physical size of the mistake, not whether it is positive or negative. In everyday language, this formula guarantees that if you keep taking steps indefinitely, the size of your mistake will eventually shrink to absolutely nothing. If a numerical method satisfies this equation, we can trust that it will eventually find the correct answer. So, we have established what it means to converge. This brings us to an equally important question. How fast are we converging? Knowing that a method will eventually find the right answer is great, but if it takes a million steps, it might be useless for real-world problems. We measure this speed by comparing the error at our next step to the error at our current step. This relationship defines the efficiency of our method. We generally look at two types of speed. Linear convergence is steady. The error shrinks by a constant fraction each time, like being cut in half. Quadratic convergence is explosive. The error is squared at each step, meaning the number of correct decimal places doubles very quickly. Now that we understand why speed matters, let us look at the formula that defines it. This is the most important equation in convergence analysis. On the left, we have the size of the error at our next guess. On the right, we have the size of our current error raised to a power q and multiplied by a constant c. The letter q is the order of convergence. It dictates the speed. If q equals 1, the method is linear. If q equals 2, the method is quadratic. As q increases, the error shrinks drastically faster because raising a small decibel error to a higher power makes it vanish much more quickly. Let us see how this plays out with some actual numbers. Before we move on, let us see this with a concrete example of linear convergence. Suppose we are using a method where the next error is exactly half of the current error. We are given an initial error of 0.8, a constant c of 0.5, and an order q of 1. We want to find the error after two steps. We begin by setting up the equation for the very first step. We substitute our initial error of 0.8 into the formula. Because Q is 1, we just multiply 0.8 by 0.5. This gives us an error of 0.4 after one step. Our mistake has successfully been cut in half. Now that we have the error for step 1, we continue to step 2. We take our new, smaller error of 0.4 and plug it back into the exact same equation. The constant 0.5 and the power of 1 do not change. We multiply 0.5 by 0.4. This gives us our final answer for this example, an error of 0.2. This demonstrates exactly how linear convergence behaves in practice. The error is steadily and predictably dropping by half each time we run the calculation. It is highly reliable, but as we can see, it might take quite a few more steps to reach an error that is truly close to zero. Now, let us contrast that by looking at a much faster mathematical tool, like Newton's method, which features quadratic convergence. Here, the rule is that the next error is the square of the current error. We are given an initial error of 0.1, a constant c of 1, and an order q of 2. We set up the equation for the first step. We take our initial error of 0.1 and raise it to the second power. Squaring 0.1 gives us 0.01. After just one single step, the error has dropped dramatically. We have gained an extra decimal place of accuracy immediately. Let us see what happens in the next step. Continuing with our quadratic method, we set up the equation for the second step. We take the tiny error we just found, 0.01, and feed it back into the machine. We must square this number. Because squaring a small decimal makes it even smaller, we expect a drastic reduction. 0.01 squared gives us a final answer of 0.0001. Notice how incredibly fast this is compared to the linear example. In just 2 steps, the number of correct decimal places doubled from 1 to 2 and then to 4. This explosive speed is exactly why engineers and scientists highly desire quadratic convergence for complex calculations. So, we have seen the math, but why does this matter in the real world? Imagine you are programming the navigation system for a self-driving car. The car's computer must constantly solve complex equations to predict where pedestrians will be in the next second. If the numerical method used to solve these equations diverges, the car's predictions will be completely wrong, leading to a dangerous crash. If the method converges but does so too slowly, like a slow linear method, the car might take 5 seconds to calculate a safe path, which is far too late. Convergence analysis allows engineers to guarantee that the computer will find the correct answer safely and prove exactly how many milliseconds it will take. To truly appreciate the difference, let us look at this graph, comparing the two methods. On the horizontal axis, we have the number of iterations or steps taken. On the vertical axis, we have the size of the error. Both methods start at the same initial error of 1.0. Notice the top curve, representing linear convergence. It slopes downward steadily, eventually reaching the bottom, but it takes many steps to get there. Now look at the dashed curve for quadratic convergence. It dives downward aggressively, smashing into the zero line almost immediately. This visualizes exactly why analyzing the order of convergence is so critical. It tells us exactly how much computing time and memory we save by choosing a better algorithm. We have covered a lot of ground today, so let us summarize the key takeaways. First, convergence is the mathematical guarantee that our numerical guessing game will actually end with the correct answer. We define this by ensuring the error shrinks to zero as the number of steps goes to infinity. Second, we learned that speed is just as important as accuracy. The order of convergence measures exactly how quickly that error vanishes. Finally, we saw that choosing a method with a higher order, like quadratic over linear, results in an explosive increase in speed, saving critical computing time. You now understand the foundation of how computers safely and efficiently solve complex math problems. Great job!